Good morning, Matt. Oh, it's been a while. I need to remember which buttons to press. Morning, Adil. I hope you guys had a relatively relaxing week for this class. I don't know. Hopefully you felt a little refreshed. Maybe not. I don't know what other classes you have. I know there was a physics midterm this weekend, so maybe not. Morning brain fog. Matt got a COVID shot. I have my first scheduled for Thursday. It's very exciting. There's hope. There's hope for the other side of this. Good morning, Joey. Although, I'm not gonna lie, this semester has been great. I'm just gonna be different going back into the classroom. JR, okay, feeling good after physics. That's good. That's good. This is the third time, I guess, physics exams have been administered via remote, so hopefully starting to get an understanding about what that means. Yeah, I mean, I don't know. This semester's been really good. Granted, I only have one class to take care of, but I've enjoyed teaching via Twitch and being a part of Discord. Had some fun on Friday night. Woohoo! And gotta love an internet troll. Yeah. You know, how are you guys doing? Just in general. Managing. We are in week 10. That means there's only a third of the semester left. We are getting there. Oh, some idiot got onto the server and was posting just inappropriate comments. Thankfully, someone notified me right away, and I took him off. But I mean, it's been fine. Not as kind as John Cena. Haven't seen John Cena in a while. I wonder how his semester's going. Yeah, tired. That's understandable. Absolutely understandable. Yeah, we're on the back end. We're on the back end. We are getting there. How's the homework? Did you guys feel like... Did you feel like you needed a lecture for the homework? Do you feel like you managed it? Matt, you're a sophomore. Joey's a freshman. So maybe not. I don't know. Let's see. What am I looking at? Yeah. Do you guys feel like you needed a lecture for the homework? Or do you guys feel like it's manageable? Like I said, a lot of it was just review from physics. I'm going to go over a couple things. That's a really good question, JR. What we're going to do in lecture is a lot of examples. So I'm going to talk a little bit about vectors and a little bit of stuff that I mentioned or that I should have mentioned in the video. I didn't feel like we needed to do that. So you don't necessarily need to take notes. There's a lot in examples. The notes, I would say taking notes would be during the recorded videos. That would probably be where you would take notes. Whereas in lecture, a lot of it's just, I'm just gonna be doing examples. So it's just a lot of writing. I wouldn't necessarily say you need to take notes during lecture, take notes during the recorded videos. In lecture, you can write down the examples and try and maybe do them yourself. But I don't necessarily think you need to take written notes per se during the Twitch lectures, maybe during the recorded videos. I mean, it's up to you. You'll see how today goes. Today is going to be a pretty good indicator of how the rest of the lectures are going to go. Matt, yes, that's a really good point. Matt, I think you're MAE, mechanical aerospace, one of those. A lot of you guys are going to see this material in MATLAB in your junior year. So there's a decent amount of you guys that are freshmen. There's a big portion of the students are freshman MAE students. You're not really going to see MATLAB in your sophomore year. So you're not really going to see this material again until junior year. That does not mean you can forget it. It is very important material for you to remember, so make sure you're getting the MATLAB material. Make sure you have some sort of practice. Use it as much as you can in your sophomore level courses. We're going to be solving systems of equations from here until what feels like eternity. You're going to be solving systems of equations in your sophomore level courses. You'll see it. Try to use MATLAB as much as possible in your sophomore year. You're typically not required, but you will see this material in junior year, and it's really, 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 really important that you do remember it, that you do practice it. I had an MAE professor, I was talking to him a couple weeks ago, just for something else, and he heard I teach 230, and he looked at me, he's like, Dr. Hammond, please stress to your students they need to know MATLAB. So even if you're MAE, it's really important that you don't just get by with the material, and maybe that's fine now, but make sure you practice it, make sure you reinforce it somehow during your sophomore year, because you're gonna need it. Yes, you will have access to MATLAB from now until you essentially graduate from UB. Chemical engineering as well. I don't know what other courses in chemical you need. I don't know if they use them in their sophomore level courses. I'm not as familiar with the Chem-E program, but you definitely need chemical, or you definitely need MATLAB for chemical engineering. Okay, so JC, good question. Midterms, they were supposed to be graded by today. They are not. There's one problem that needs to still be graded for at least my sections. I'm going to go through them all. I'm going to go through all the problems today. I'm going to take notes on what the grades were by question. I'm hoping everything will be done by tomorrow, but I want to make sure that all of the grades are complete. A couple students in their homeworks have been like, my problem wasn't graded, and I don't want that to happen for the midterm. So I'm hoping by tomorrow. Yeah, I'm hoping by tomorrow. It should be done by tomorrow. Sorry about that. Other announcements. I think that's it. Okay, let's go ahead and begin. So most of these lectures for linear algebra are going to be written. We're not really going to visit MATLAB as extensively anymore. A lot of it, I'm just going to do a lot of writing. And that's what you're going to be doing for your homework. For your project, you're going to still be doing MATLAB. I created videos for each of those parts, so make sure you go into that programming project folder and watch those videos if you get stuck. The Wilcox whatever on the Discord this weekend spent like the entire weekend doing the programming project. It looks like he got pretty far, which is great. So it's not impossible, it's just time consuming. So if you're stuck on something, go to watch those videos. Come to Friday office hours. There were about 10 people in office hours on Friday. So come to those. The project is doable. I think it is much more doable this year than it has been in the past. But I created those resources, so make sure you're looking at those for the project. Okay, so homework 9. Homework 9 is due on Wednesday. Just a couple of things to point out. When it says find a non-zero vector x that is perpendicular to w, perpendicular means it's right angle. So when you have perpendicular, use your angle formula. Angle between, that's not how you spell between. Between two vectors. So essentially, if they're perpendicular, you have the cosine theta equals u dot v over the magnitude of u times the magnitude of v. So the angle here should be 90 degrees. In reality, this is going to be equal to 0. And so this is really the formula you should be using for perpendicular vectors. This table shows this orthogonal vectors. So I forgot to mention, this here is just Pythagorean's theorem for vectors. Here's u, here's v, here's u minus v. So it's just a formula. But when you're talking about the angle between two vectors, you can just use your angle between two vectors with theta equals 90 for orthogonal vectors. Other questions I've gotten. Oh, this one here. Determine D. Determine if vector W is a linear combination of the vectors x and y. You set it up as what's called a linear combination, where you have a scalar, c1 times a vector, in this instance x, plus c2 times a vector y equals another vector, in this instance w. So you set it up like this, plug in x, plug in y, plug in w, you multiply through, so you're going to get essentially 4 different equations, and we'll see this in various forms today, but you'll get 4 different equations that you can use to solve for c1 and c2. And then also, confirm your answers here. You can also use the a cos functions. I will update the homework document. I need to make a note of that. I think those are the biggest questions that I got. Yes. Okay. In this one? Why is the first uv under the square root not italicizing the distance between two vectors? Distance between two vectors. I don't know. Mistake. That should be italicized. Mistake. I can go fix it. Yeah. Okay. So, let's talk a little bit about this week material. Zoom in a little bit. So the goal of this week material, and really moving forward, is we're starting to look at systems of equations. And you've seen this before. We talked about this and introduced this back in week 4 or whatever it was, where we're starting to look at systems of equations. So the nice thing is we can view systems of equations as vectors. And that's why we're talking about vectors for linear algebra. Vectors are composed of any set of numbers. It's just a single row or a single column of any set of numbers. You can think about it graphically for 2 dimensions and 3 dimensions. But if you get past more dimensions, you kind of got to get away from thinking about it graphically. But really, it's really just an ND space. And each equation can be viewed as a line or a plane or whatever, something in that ND space. So if we look at it from 2 dimensions, it looks something like this. So here I have 3x plus 2y equals 12, 2x minus 2y equals negative 2. So we can solve the system in a couple different ways. I can use substitution. So we'll get to graphical representation in a minute. But I can use substitution. And you guys have been solving system equations for a while. Most of the time, you're probably using substitution, where if I do this, let's see, this second equation is really x equals negative 1 plus y. I can solve for x. Let me move this down. No. There we go. And then I can plug it into my first one. I solved a bunch of things this weekend so that I didn't make math errors. Spent so much time yesterday. So 3, negative 1 plus y plus 2y equals 12. And when I do that, I can solve for it, and I can say negative 3 plus 3y. Yeah. Shoot, did I make a mistake? Look at that. I did make a math error. Plus 2y equals 12. Told myself I wasn't going to make math errors. And I did. So 5y equals 15, y equals 3. Once I have that, I can go plug it in up here and say x equals -1 plus 3, or x equals 2. So we know we can solve things using substitution, and we can also solve things using elimination. So hopefully you know both of these methods. My first equation was 3x plus 2y equals 12, positive 12. My second equation was 2x minus 2y equals -2. If I add these two equations together, I get 5x plus 0y equals 10. So essentially what we're doing when we do elimination is we are replacing an equation by adding two equations together. So now my new system looks like this: 3x plus 2y equals 12, and then 5x equals 10. And it doesn't matter which one I replace. But now here's my new system, and I can easily solve for x here. X is going to be 2. And I can plug that in up here and solve for y, which gives me 3 times 2 plus 2y equals 12, or y equals 3. So notice I got the same solution regardless of which one I used. I can also think about this system, or I can also rewrite, I can also rewrite this system in a couple different ways. If I think about it as two equations, essentially we're thinking about it in terms of lines. This is where we go back to the graphical representation. So if I graph these two lines, I end up with something like this. And please excuse my beautiful drawings. Okay, so you do not need to use graph paper for your homeworks. You're not required to use a specific kind of paper. Sometimes it helps, sometimes it doesn't. I will draw on, I will have lined paper for our examples just so I can help orient my drawings, but you do not need to have lined paper for anything. If you can see, all of my work for practice is not on lined paper. Just make it look neat. Okay, so this first equation, the second equation looks like this. Once again, not pretty. Where it's 2x minus 2y equals -2. And then my second one looks like something like this. Hold on. That's not how that goes. That's a little better. My second one looks like this, where it's 3x plus 2y equals 12. And if I look at that intersection point, it's supposed to be at 2, 3. That gives me my answer. So I can think about each line, or each equation, as a line. That's traditionally how we're looking at equations. However, I can look at them as vectors as well. So what we can do is we can rewrite our system of equations in a couple different forms. So we've got our traditional line form. We can also view them as vectors, or a linear combination, where if this is my original system, I can view it as the numbers in front of x, so 3 times 2, or 3, 2 in front of x. Those are my numbers in front of x. Plus my numbers in front of y, 2, -2, equals my values on my right-hand side, 12, -2. So I can view this system as what's called a linear combination. A scalar times a vector plus a scalar times a vector plus a scalar times a vector, etc. equals another vector. So here I can view my system as a linear combination, or where I have a bunch of vectors instead of lines. So if I graphed this, it would look like this. Okay, so my x vector is 3, 2, which goes out to here. So here's my x vector, the one in front of x. My y vector is 2, negative 2. It looks like this. And then my b vector, we'll call this my b vector. So here's my x vector, here's my y vector. My b vector, it goes all the way out here. 12, 2, so that one was 12. Negative 2 goes out to here. Okay. Okay, there's my b vector. So essentially, when we have a linear combination, we are extending my vectors along this axis. Ooh, that's not on the right spot. So I'm saying I'm going to scale this vector by some constant. I'm either going to make it longer by scaling it by a value greater than 1, or I'm going to make it shorter by scaling it by a value less than 1. For this system, essentially, I know, because I've solved it 3 other ways now, that I'm scaling this vector by 2. So I'm essentially multiplying this vector by 2. So it extends up to here. So 2x, or 2 that vector. And then for y, my y vector, I'm scaling it by 3, because I know my system, y is 3. So 1, 2, something like that. So here's 2 times 2, and here's times 3. So essentially, when we're looking at our system of equations in terms of vectors, we are scaling them, extending them along this line, so that when I add them together, I end up at b. So here is 2 times my y vector, and here's, 3 times my y vector, and here's 2 times my x vector. So here's my original y vector, this one right here, 2, negative 2. Multiply it by 2 out to here. No. And multiply it by 3 out to here. And then I add to it my x vector multiplied by 2. So here's my x vector multiplied by 1. Here's my x vector multiplied by 2. So I'm adding my vectors together. So this is another way that we can view systems of equations, as a bunch of vectors. Technically, this is also a bunch of vectors, where each row is considered a vector. 3, 2, 12. So that's from equation 1, equation 2, to negative 2, negative 2. So we're trying to shift our thinking from thinking about individual lines, individual equations, to thinking about them as vectors. Someone asked in the questions, why are we spending so much time solving different systems of equations? And part of it is because this class is called Engineering Computations. We're looking at different ways to compute, to solve things. A lot of engineering is systems of equations. A lot of times you don't realize you're using system of equations until later on. A lot of things in your undergraduate program, you don't necessarily need to view them as system of equations, and it's not always presented as a system of equations. But behind the scenes, you're really manipulating systems of equations. I know when I got to grad school, I was just amazed at how much system of equations actually permeates a bunch of material. So it's not as relevant for undergrads, but you can, knowing this information, you can view a lot of your problems as systems of equations as you move forward in your program. Okay, so we can view equations as lines, we can view them as vectors, and then we can also write things in matrix form, which we've already seen, where I can say 3, 2, 2, negative 2, so here's A, X is my vector of unknowns, X, Y, and then B is my equation on my constants on my right-hand side. So there's many ways that we can write a system of equations, and different ones will give us different information. We can view it as lines, we can view them as vectors, and we can view them in matrix form. Most of moving forward, we will view things in matrix form. Okay, so this will become secondhand nature to you guys. You will see it over and over and over and over and over again. I went to grad school at the University of Iowa, in Iowa City, Iowa. there are not enough Iowas in there. It was a good school. Really, you go to grad school, it's not always necessarily where you go to grad school that matters, but who's your mentor? What work do you want to get into? I went for medical imaging, and there's a huge medical imaging core, a group of people at Iowa. Yeah. Okay, so that's some background on systems equations. So like I said, we are going to solve systems equations using lots of different methods. I actually programmed all of these methods in MATLAB one day. It was very exciting and very happy. It was a great day. So I'm going to show you guys how we solve them on paper. And on paper, you have a little bit more flexibility, a little bit more freedom. I'm also going to show you guys how we can solve them algorithmically and show you what my program looks like in order to do that, which will involve MATLAB. Okay, so the first method that we are going to use is called Gauss elimination with back substitution. And in reality, Gauss elimination with back substitution is just elimination. So if I wrote this equation in matrix form, it would look like this. 3, 2, 2, negative 2. X, Y equals B. And we know that it doesn't matter what these are called. It doesn't matter what X and Y are. They're just unknowns. It could be XY, it could be X1, X2. You'll see those are the two most common that you'll see in this class. It could be ABC. It really doesn't matter what goes in this X vector, as long as we know that it's unknown 1 and unknown 2, or unknown 1, unknown 2, unknown 3, unknown 4, whatever. Just as long as they're in the right order. So typically what we do is we write what's called an augmented matrix, where we just kind of remove that from the system, and we just write our constants. So 3, 2, 12, and then 2, negative 2, negative 2. And typically we have this line here to distinguish between the fact that this side is A and this side is B. So if I look at the steps I did for elimination, I'm going to do those same steps on my, what's called an augmented matrix. This is my augmented matrix, where A is placed right next to B. So what I did is I just added these two equations together to replace my second equation. So essentially all I did was I left this one alone. And then when I added these two equations together up here, I replaced my second equation. So this was my new system. So I did 3 plus 2, which was 5, 2, or negative 2 plus 2, which was 0, and then negative 2 plus 12, which was 10. So this became my new system. So here I took row 2, and I said row 1 plus row 2. So I replaced row 2 by adding row 1 and row 2. And the nice thing is given this new augmented matrix, I can just rewrite my system equations again by saying 5 unknown 1 plus 0 equals 10. Same thing here. 3 unknown 1 plus 2 unknown 2 equals 12. So you should get comfortable between seeing a system of equations in augmented form and in our equation form. So you should be able to go back and forth between them. Each row in my matrix here on this side is really just an equation, where it's 3 times my first unknown plus 2 times my second unknown equals my B value. Once I have this here, then I can just easily solve my system, easily solve my unknown just like I did up here. This tells me that X equals 2, I can plug it into here and say Y equals 3. This is the process of Gauss elimination with back substitution. It's just elimination, the same elimination we've done since whenever you took algebra, I think. I don't know, whenever you first learned that method. Except now we're going to do it in a matrix form. Some of you guys may have seen this in high school. Some of you guys may have not. That's fine. We'll go through a bunch of examples. As many as we can. Okay, so let's go ahead and, before I forget, there's in your homework, there's this definition called trivial and non-trivial. I didn't put it in the notes. I think it's later on in the notes, in like week D. But when it says trivial solution, it means that your unknowns are 0. So it means that x equals 0, y equals 0, z equals 0, x1 equals 0, x2 equals 0, x3 equals 0. Whatever they are, they're all 0. Because we know that 0 times 0, or 0 plus 0 plus 0 plus 0 equals 0. That's called a trivial solution. A non-trivial solution is when they're not all 0. So you could have x equals 0, but y equals 1. But they're all not 0, or they're not all 0. And that's what that means when it says trivial versus non-trivial. Forgot to mention that in the notes. And it's in your homework. Okay, so let's solve this system using what's called Gauss elimination with back substitution. So your first step is always to write your augmented matrix. So that was in your quiz. Step 1, write your system equations in an augmented matrix. So we've got our A. My first equation is 3, 5, negative 2. I'm going to draw my line here and get my B, negative 15. Okay, you could write out AX equals B and then put your augmented matrix together. You will get more comfortable flowing between all of these three. So let me do it. AX equals B. So here's A, X, negative 15. Okay. My second equation, I have a 4 in front of the X, a 1 in front of the Y, a 1 in front of the Z, and a 21 in my B. My third equation, I have a negative 4 in front of the X, negative 4 in front of the Y, and a 5 in front of the Z, 21 in my B. Okay, so here it is in AX equals B. My augmented matrix looks the same, except I take out my all this, draw a line, and then put B right next to it. Now when I do what's called row operations, when I do my eliminations, I'm doing it on my augmented matrix. So with Gauss elimination with back substitution, our goal is to perform elimination steps until we have an equation with 1 unknown, an equation with 2 unknowns, and then an equation with 3 unknowns. So typically for this, we are going to find what's called our lower triangle of zeros. So my goal is to end up with a 0 here, a 0 here, and a 0 here. I want to eliminate those 3 locations, just like we did with this problem. Oh, here it is. Just like we did with this problem. Here I have one equation with 1 unknown, and then an equation with 2 unknowns. So I can easily solve for 1 unknown using this equation, and then solve my other unknown using this equation. The same goal, typically though, we do it in an organized fashion where I find what's called a lower triangle of zeros. So I want to make this a 0, this a 0, and this a 0. And I have 3 rules I can use. Those are your row operations that I talked about in the videos. I can exchange rows, I can swap 2 rows. It doesn't really matter, it's the same system. As long as I do the entire thing, or the operation to the entire row, I can multiply a row by a constant, and I can replace a row by adding it to another row. Okay, so I'm going to start by doing it in my algorithmic form. So that means I'm going to start by doing the same process for this matrix as I would on any other matrix. And that is by starting to put a 0 in my first column. So I want this to be 0 and this to be 0. And what I'm going to do is I'm going to use this number here in order to make that a 0. So my goal is to add equations together so that I end up with a 0 here and a 0 here. To do the first one, to make a 0 here, what I'm going to do is I'm going to make sure that this number and this number are the same so that I can subtract them. So first thing I'm going to do is I'm going to multiply row 1 by 4. So row 1 is going to equal row 1 times 4, and then I'm going to multiply row 2 times 3. When I do that, I end up with this: 12, 20, negative 8, negative 60, And row 2 becomes 12, 3, 3, and 63. And row 3 didn't change. It was still -4, -4, 5, 21. These problems take a while, mostly because you're writing a million things. You're writing so much. And also, I like to say linear algebra is really just multiplication and addition. That's really what it is. You just multiply and add a bunch of things, but you're doing it so often. So there's a lot of places where you can make the sign error. There's a lot of places where you can make a multiplication error. So make sure you're writing things out. Make sure you are explicitly showing what you're trying to do. And so this one, I multiplied row 1 by 4 and I multiplied row 2 by 3. My goal was to make sure that these two numbers end up the same so that I can add or subtract my equations together to make sure that I get a 0. Okay, so now I'm going to take row 2 and I'm going to say row 2 equals row 2 minus row 1. So row 1 doesn't change, so row 1 is still 12, 20, -8, -60. And row 2 is now 12 minus 12, which is 0, 3 minus 20, which is -17, 3 minus -8, which is 11, and then 63 minus -60, or 123, and then row 3 doesn't change. Row 3 is still -4, 5, 21. So JR, I will show you that. I'm showing you as the algorithmic steps. So like these steps will always get you to your answer. You can choose differently, and I'll show you that next. But this one, my goal was to get a 0 here. So if you always start by putting a 0 in this spot, using these two numbers, that's always a good start. You don't have to always start here. You have more freedom as a human, but I'm showing you these steps you can apply every single time. Okay, so my next goal is to get this a 0. So I got this a 0, check. I did that one. My next goal is to get this a 0. So in order to do that, I'm going to add this equation and this equation, equation 1 and equation 3. But first I need to get equation 3 to have the same number as my number in equation 1. I need these two to have the same number so I can add them together. So I'm going to take row 3 equals row 3 times 3. So when I do that, 12, 20, -8, -60, row 1 doesn't change. Row 2 doesn't change. And now -4 times 3 is -12, -12, 15, and 63. So now I can take these two numbers, these two rows, and add them together. Yes, so JR, yeah, we're generalizing process. Why couldn't we just multiply row 3 by row 2? So you cannot multiply a row by a row. You can add them together. And like I said, I will show you that in a minute. I'm showing you the general process that will work every single time. Okay, so now I can say row 3 equals row 3 plus row 1. So row 1 doesn't change. Row 2 isn't going to change. Now I'm saying -12 plus 12, which is 0, -12 plus 20, which is 8, 15, plus 8, plus -8 is 7, and then 63 plus -6 is 3. So now I have a 0 here, and I have a 0 here. My last one is to get a 0 here. Let's move that one down. Move down. No, come on. There we go. So my last goal is to get a 0 here. So the way I'm going to get a 0 there is by adding row 2 to row 3. So now I need these two numbers to be the same. So I'm going to take row 2, and I'm going to multiply it by 8. I'm going to take row 3, and I'm going to multiply it by 17. So row 1 doesn't change. Row 2 times 8, 0 times 8 is 0. 17 times 8 is 136. 11 times 8 is 88. Why do I have a sign difference? And 123 times 8 is 984. Oh, shoot. This should be negative 17. There we go. Like I said, there's lots of little places where you can make errors. Matthew, yes, you are. I'm showing it, breaking it up step by step. As you do this, you will be more comfortable with showing multiple steps in one operation. And I will get there as we move along. I'm just breaking it up to show essentially everything that we're doing. Okay, so then row 3 times 17, I have 0, positive 136, there we go, 119, and 51. So now I can say row 3 is going to be row 3 plus row 2. So row 1 isn't going to change. Row 2 doesn't change. And now I can say 0 plus 0. 136 plus negative 136 is 0. 119 plus 88 is 207. And then 51 plus 984 is 1035. You do not have to deal with whole numbers. I prefer to deal with whole numbers. You can deal with fractions. The thing with Gauss elimination, with back substitution, is we all could use a completely different process and end up with a different system down here, with a different result, but still get the same answers for our unknowns. Okay, so notice I have a 0 here, I have a 0 here, I have a 0 here. I have my system of equations. This one has 1 unknown, this one has 2 unknowns, and this one has 3 unknowns. So if I rewrite my system like this, I end up with 207z equals 1035. I get negative 136y plus 88z equals 984. And this one is 12x plus 20y minus 8z equals negative 60. And now I can just solve for my unknowns. This tells me that z equals 5. 1035 divided by 207 is 5. If I plug that into this equation, I get y equal to negative 4. And if I plug both of those into this equation, I get x equals 5. So one key thing is this this matrix right here is called REF, reduced echelon form. So someone mentioned, JR mentioned, why do we need to eliminate those specific locations as long as we get the correct number of unknowns in each row? This is traditionally REF, reduced echelon form, where we end up with this lower triangle of zeros. So it doesn't really matter which rows you eliminate, which positions you eliminate, as long as you end up with a lower triangle of zeros at the end of the day. So if you ended up with this one having 2 zeros and 1 unknown, then that's fine. You would just rearrange your equations. Keep in mind though, we need to end up with a lower triangle of zeros. So if we're talking about REF, there needs to be that lower triangle of zeros, where one equation has 1 unknown, that's our third unknown. One equation has 2 unknowns, where it's our last 2 unknowns, and then one has all 3 unknowns. So given a system of equations, you can do any row operations you want as long as it's valid, and end up with your lower triangle of zeros. So we all might get different row echelon forms. Let's do this one again, except we'll do a different process. So like I said, that was our general process. First, we can find this, we can make this one a 0. That should be a 4. We can make this a 0 using this equation. Then we can make this one a 0 using this equation. And then make this one a 0 using this equation, whatever that number ends up being. And that's our general process. That will apply every single time. However, as a human, you don't have to do it that way. You can kind of pick and choose what you're going to do. You have a lot more flexibility. So I could do this system by saying, okay, so first I recognize that 4 and -4, those are the same number. So I'm going to make this a 0 right away by saying row 3 equals row 3 plus row 2. So row 1 doesn't change. Row 2 doesn't change. But now row 3 is going to be -4 plus 4, which is 0. 4 plus 1. Shoot. I might have to wing this one. I did it differently. That's okay. 4 plus 1, which is 5. 5 plus 1, which is 6. 21 plus 21, which is 42. So now I have a 0 here. Okay, so that's great. Now I can make this a 0. Notice I only have one option now. I have to use this 3 in order to make this a 0 by adding these two numbers together, these two rows together. I can't use this 0 anymore. The 0 is kind of static. Once you have a 0 in a location that you want, don't change it. Don't move it. You will get more practice as you go along. So I want to make this 4 a 0. So I'm going to say that row 2 is going to be 4 times row 1 minus 3 times row 2. So now I'm combining multiple steps rather than multiplying things out separately. So I added them together. There's a plus here. Oh, yeah, it is a -4. Sorry. So -3. Thank you. I dropped that when I erased. So now I'm adding multiple steps. You can break them up as much as you want. It's easier to keep track of everything you're doing over here on this side by breaking it up into individual steps. If you do it like this, that's fine, you can, but make sure you're a little more explicit about what you're doing. So it would be row 1 doesn't change. 3, 5, -2, -15. Row 3 doesn't change. 0, -3, 6, 42. But now I'm saying 4 times row 1. So 4 times 3, which is 12, minus 3 times row 2, or -12. And then I'm saying 4 times 5, 20, minus 3 times 1, which is 3. 4 times -2, which is -8, minus 3 times 3 times 1. 4 times -15, minus 3 times 21. So there's lots of places where you can make a small sign error, where you can make a mistake. So the more complicated your row operations get, the more you combine steps, the more work you need to show. So when I multiply this out, I end up with this. And notice, it's just multiplication and addition, or subtraction. It's really not that complicated. There's just a lot of it. Knowing where the numbers are coming from, you can make small little mistakes, little sign errors. So 12 minus 12 is 0. 20 minus 3 is 17. 8 minus 3 is -11. And then 60 minus 63 is -123. So I've got my 0 here. I've got my 0 here. I didn't follow the same steps I did over here, but I still have zeros in those locations. So there's multiple ways that you can move forward. You don't have to use the same row operations every time. This method we showed over here, I showed over here, where you find this 0 first, and then this one, and then this one. That works every time. That will always get you to where you need to go. Just your row operations look different depending on what constants you need, what numbers you need to multiply your rows by. This process over here is a little bit more freeform. You can pick and choose what you want to do. As a human, you can easily see that if I take 4 and add it to -4, I'm going to get a 0. You could replace row 3 right away. You could replace row 2 right away. As long as you are doing valid operations, getting our valid zeros in the locations we want, it doesn't matter. Okay, so once I have this one, I have my first 2 zeros. That's great. Now I want to get this to be a 0. And I've got 2 options. I can either use this number or I can use this number. Keep in mind, though, once you have a 0 where you want it to be, you don't want it to change. So if I use this number, I'm going to add my 2 rows together. I get 0 plus 0. That's great. I can keep a 0 there. If I use this number, though, I would get 3 plus 0, and I would get a 3. So as you move through your row operations, you'll get more comfortable with choosing which ones to choose. I really should only use this one, so I maintain the 0. So I'm going to take row 3, and I'm going to replace row 3 by saying 17 row 3 plus 3 times row 2. So row 1's not going to change. 3, 5, -2, -15. Row 2 doesn't change. Note, I am using row 2. I'm not changing row 2. I am taking row 2 and I'm adding it to row 3, but row 2 does not change. Only row 3 changes. So when you write out your row operations, be explicit about what you are doing. I'm replacing row 3 by saying row 3 equals 17 row 2, or 17 row 3 plus 3 times row 2. You can't replace row 1 by adding row 3 and row 2. So when you replace a row, it needs to be involved in your addition or subtraction. Okay, so 17 times 0 plus 3 times 0 is 0. I maintained my 0 there. That's what I wanted. Check. Then I have 17 times -3. Pull out your handy dandy calculator. 17 times 3 is -51. I knew that. Plus 51. 3 times 17. 17 times 6 should be 102. Plus -33. 17 times 6 is 102. Plus 3 times -123, or -369. Row 1 doesn't change. Row 2 doesn't change. And row 3 becomes 0, 0, like I wanted. 102 minus 33 is 69. 102 minus 369 is -267. If I did my math right, this system of equations where 69z equals -267, 17y minus 11z equals -123, 3x plus 5y minus 2z equals -15. If I did my math right, this solution should match exactly what I got down here. Okay, so first I can find z. -267 divided by 69. Nope, I did not do my math right. Crap. 69 times 5, 345. I probably have a sign wrong somewhere. Or I forgot to write a number. Right, this is supposed to be 42. There we go. So 42 times 17. 714. There we go. 714 minus 369. That's what I wanted. This should be 345. That was an easy find. That was a very easy find. Usually, when you get something incorrect, it is not that easy to figure out where you did something wrong. That's why it's very important that you show your work. You show as many steps as you can. Okay, so when you solve for this, 345, positive 345 divided by 69, There we go, there's my 5. So z equals 5, and then you can plug in and solve for y, and plug in and solve for x. Okay, we are out of time, but I wanted to show you guys my MATLAB program for this. So if I go to MATLAB, please tell me, yep, there we go. So when you solve for MATLAB, this is what my function looks like. Like I said, I spent Friday, I think, writing algorithms for all the linear algebra stuff. It was very exciting. I was so excited. So I wrote a function. It's called Gauss elimination. These ones here are the first non-zero entry in a row is called a pivot. So for every row, so I want to go through all of the rows below the first one. So 1, size of A1 minus 1. So I'm checking to see if there's a 0 in that location. You'll notice as you go along, if there's a 0 in, here, let me go back. If there's a 0 in this spot here, then you can't use it to make zeros here and here. So you can't have a 0 and it's called the pivot location. This is a pivot, this is a pivot. You can't have a 0 there. Like if this ended up being 0, it wouldn't work. You couldn't use it to make this a 0 because 0 plus anything is anything. You can't eliminate anything. So my algorithm in MATLAB just checks to see if it's a 0. Checks to see if there's a 0 there. If there is, it just swaps the rows. Here's where it does the elimination step. I wrote another function that does the row operations. So you enter in your A matrix, whatever type you want, and then various amounts of information. I use some advanced MATLAB techniques for this, but whatever number of arguments that determine if it's row operation type 1, swapping 2 rows, row operation type 2, where you multiply row by constant, or row operation type 3, where we're doing that elimination step. So here's my elimination step. So here's my A matrix. I'm doing row operation type 3. I'm multiplying row whatever, row 1, or row, whatever row I'm on, by some constant. Here's my constant that determines what's going to do that elimination. It's based on whatever that pivot location is. So here's my pivot location, and whatever value is in my row. So if I go back to my notes, it's based on what are these two numbers? What are these two numbers? So whatever's in my pivot plus whatever is originally there. That determines what my multiplier is going to be for a given row. And you'll see this as we go along, as you do a lot of practice. So I'm doing my elimination step, and then here's where I perform my back substitution, where I take my last equation, the bottom one for my last row, and then I work my way up. So this took a little bit of thinking. The more you do these problems, the more you'll begin to see this algorithm that comes out. We will do more examples on Wednesday. Like I said, they just take a long time. I solved equations for way too long this weekend. Way too long. Okay. So we are out of time, like usual. Yeah. So I'll see you guys on Wednesday, where we do Gauss elimination, Gauss-Jordan. We'll look at inverse. Hopefully we'll get through at least 3 more examples. Okay, any final questions? Okay, with that, I'm gonna jump over to office hours. Don't forget, watch the videos for the programming project. I tried to make them helpful. They do go through some key information that will help. So make sure you do that. And I will see you guys on Wednesday. Welcome back.